Hello, I'm Ferdubati, and this is a lecture on linear regression for Data 630. So in this lecture, we will cover simple linear regression, which involves only one regressor and one response variable. Then we move on to multiple regression, which is an extension of simple linear regression containing multiple predictors with a single response. And we cover the model fitting process, how we actually fit the model, and evaluating the model fit, which is a goodness of fit, and some of the potential linear regression issue that you should be aware of and consider when using linear fit. Regression is a way to measure the strengths between one dependent variable and a set of independent variables. Now, throughout this lecture, I refer to the dependent variables either as target variable or response variable, and the independent variable as explanatory, predictors, and regressors. These terms are unanimous, and people from different domains have a preference to one term over another, but they mean the same thing. So what does a linear regression model? It models the expected value of a numeric quantity. That means it's the dependent variable or the target variable is a numeric variable, while the explanatory variables can be numeric or categorical or any combination of the two variables, these types of variables. So the independent variables are basically input variables and can take many different values, while the dependent variable changes as a consequence of the changes in independent variables. Okay? And as for the application, regression can be used primarily in two different ways. One is as a prediction tool. That means the focus in the prediction application is you want to predict or forecast the numerical value without focusing on the underlying relation between the dependent variables and the independent variables. In another application, which is called advice, is what you are interested in the form of the function or how individual variables or explanatory variables are related to the response variable and the strings of the relationship or the nature of the relationship. So that kind of application where you need to have some understanding about the underlying relationship is advice. Mathematically, the relation between the regressor and the response is expressed like this. So the y, the response variable, is the interceptor term beta 0 plus the slope term times the slope term beta 1 times the input variable x plus an error term. So the intercept is the mean value of y when x is 0. Okay, if the domain of x includes 0 and when x is 0, the value of the intercept becomes the value of the response variable. And the slope is a change in the mean value of y per unit change of the x value. And an important assumption in linear regression in general is the error is uncorrelated and it has a mean 0. Okay, so there is no systematic bias in one direction. So that the mean value of the error terms are 0, and then we have unknown constant variance. Okay, here graphically you can explain this. So you have x and y, the predictors and the response variable, and then this is your regression line. So for a unit change of the x value, the beta 1 of the slope determines the rate at which the response changes. So least square is by far the most common estimation technique in linear regression, and it is an optimization technique which minimizes the sum of the square difference between each observation and the value on the regression line. Okay, and although linear regression is by far the most common, there is another type of algorithm called maximum likelihood, which if certain assumptions are made, you can actually use maximum likelihood and still get the same result uh, uh, with the one that you get from least square estimator. So earlier we looked at this for the population parameter. Now once you estimated the parameters, I use these parameters and coefficient at the same, they mean the same thing. They reference to the beta terms. So here now we have an estimated quantity. So we use the term beta 0 hat plus beta 1 hat times xi plus error term for each of the observation. That means the difference between the observed value and the value on the regression line, corresponding regression line. So the i's are the index for the observation. So least square regression is minimizing the residual sum of square, which is nothing but the difference between the observed value and the estimated value of the response. And we square the difference, we sum over all the observation, and we try to minimize that. That's what least square does. And here you are plugging the estimated function here in terms instead of using the y hat here. And now it is a type of optimization technique. One common technique approach to minimize a function is, or maximize a function is, take the derivative of the function, you set it to 0. In the case of minimization, take the negative value of that, and then compute. You take the simplify for the algebra, and this is what you see here. So it's the beta 1 term is the sum of the individual response times the difference between the i's x values of the I observation and the sample mean for the x, and you sum over all the observation and divided by the total sum of square root for the regressor, xi value for the observed and the sample mean for the explanatory variable. You square that, you sum over, and then this is the beta 1 term. Now you can actually use this for a smaller data set, and you can actually test what softwares provide, for instance R. So the underlying implementation is this. So when you say the estimated value from R, this is the function that is used. And plugging some terms, and then the intercept term, which is a beta 0 hat, is calculated at the sample mean of the response minus the product of the beta 1, the slope, the estimated slope, and the sample mean of the regressor function, the regressor variable. Okay, graphically, maybe it's easier to explain it this way. Is so we have a population regression line, which we don't have access to. We don't know it. So we are estimating because we don't have the parameters. We don't know the beta 0. We don't know the beta 1, the intercept and the slope. So we have to estimate it from the observation, from the data we have, right? So applying least square estimator, the purple line is the estimated regression line. So it's not quite perfect, but very close to the population regression line. Now, one thing that you have to remember is even you are able to perfectly estimate the regression line. That means even if you have an overlapping estimated line on the regression line, you will still have an error term because it's unlikely that all the observation will lie on the regression line. So in the statistic, there are two error terms. One is the one that by improving the algorithm, the model fitting process, you can reduce it. It's called reducible error term. And there is another term that is irreducible, that regardless of how perfect your model is, there is inherent bias or inherent error term that is going to be always there. Okay, so that's least square. So regardless of what technique you use for estimating the parameters, now how accurate the estimation is also a very important part of linear regression estimation. By the way, least square is an unbiased estimator. What unbiased estimator means is that if you take multiple samples from that domain and fit multiple linear regression function, and if you take the average of those, that means the mean of the sample means, the estimated means, then they converge to the population mean. Okay, so that means if you do that enough times, you converge to the population mean, and that is usually called unbiased estimator. But how accurate is our single coefficient estimation, right? You fit a function on one sample, how accurate is that estimation is what we're discussing here. So in general, we employ a standard error to assess how far the estimated quantity, the estimated parameters are from the true value. Okay, and with the assumption of uncorrelated error term, which is a very important assumption in linear regression, when we do diagnostic and when we do some validation, it's part of that validation process where we have to make sure that the error terms are uncorrelated, because some of the outcome, some of the output is with assumption that the terms are uncorrelated. So a standard error of the intercept is given by this function here, the variance, which we don't know, this is a population variance, times 1 over n plus the sample mean square of the x value over the sum of the total, the xi's, individual xi's, and the sample mean of the x values we square and sum over it. So that is the standard error of the intercept. In the a standard error of the slope term, again, this is for the estimated function, the estimated quantities, is again the variance, the population variance, which we have to estimate because we don't know the variance, over the sum of the difference between the xi's and the sample mean square. Okay, so the variance, the population variance, is estimated as a residual standard error of this. So this is not quite an average value because the denominator is n minus 2. So this is the number of degrees of freedom that we have in the observation. So the way you calculate degrees of freedom is the difference between the number of observations you have in your sample and the number of predictors. In this case, for simple linear regression, we have two coefficients, right? Two parameters, the intercept and the slope, and that's why you see n minus 2. And this is a residual sum of square, which is a term that we looked at earlier here when we discussed about minimizing the least square. So this is RSS term, where you take the difference between the observed and the estimated, take the square of that, and sum over all the observation. Okay, and so this is the variance, and you plug this in this, and this is how we calculate the standard error. Okay. Okay, now the estimated coefficient or the parameters are point estimates. Okay, and now we want to have a level of confidence, and that is done through the confidence interval. So that means how much are we confident that the true value will fall in a given range. So so the width of the confidence interval is a measure of the overall quantity of the regression line, because the larger the variance is, that means the less useful the estimated value, because the uncertainty will be large. If you have a large confidence interval, you have much uncertainty in the estimated quantity. And if you have a narrow one, which is in general a good thing because you are more certain to, to a given confidence level about the estimated quantity. So here you see the confidence is for the intercept is plus or minus 2 times the standard error of the estimated quantity, which is the intercept, and here the same thing for the beta 1. So the estimated quantities fall between minus 2 times the standard error of that estimated coefficient and 2 times the standard coefficient, the standard error of that coefficient. So what that means is, with a repeated sample of the same size, if you take multiple samples from that domain of the sample size, 95% of the intervals will contain the true value. Okay, that means that probably there's 5% chance that they might fall outside of the confidence interval. Hypothesis testing. So after we estimate the parameters and put confidence interval in the estimated quantities, the next step is hypothesis testing. So the estimated function is statistically significant. So that's what we measured by hypothesis testing. So we need to formulate the null hypothesis. Now, this is just classical hypothesis testing methodology where you have the null hypothesis and alternate hypothesis. You use some kind of applicable set of statistic for the hypothesis, and you define a decision rule to reject or not to reject the null hypothesis. So a statistic is basically a function of a random sample. So it's a random variable, and you can discuss the distribution of that, and the characteristic of that random variable allows you to work with null and alternate hypothesis. So in order to perform a statistical test, we should know the distribution of the test statistic and under the null hypothesis. Now, in the setting where you have a normality assumption, which is the case is in the regression setting, then some variants of normal distributions such as chi-square, student t distributions are appropriate. Now here in the regression, we use a student t distribution for the test statistic. Okay, what is the null hypothesis? The null hypothesis is there is no relationship between the x and the explanatory variable and the response variable. No relationship. In the alternate hypothesis will be there is some relationship between the two. So if we cannot reject the null hypothesis, that means the estimated parameters are not significant. So we have to reject the null hypothesis of no relationship between the x and the y. And to reject the null hypothesis, you pick a confidence level. The industry standard pretty much is 95% confidence. So the alpha value will be 0.05. And we need to establish the estimated quantities are such that they are far from zero. Okay, because if the estimated parameters are zero, that means there is no relationship between, for instance, if beta 1 is 0, so there is no relationship between x and y. Okay. So to measure the number of standard deviation of the estimated quantity from 0, we compute the t statistic, which is given here, the estimated beta 1 over the standard error of beta 1, which we discussed in the previous slide. So an important component of hypothesis testing is the p-value. So the test statistic, we calculate the test statistic along with the p-value to be able to reject or determine whether the estimated quantity is significant or not. The p-value is defined as the lowest significant level at which a null hypothesis can be rejected. So, for instance, if you have a confidence, if you take 95% confidence level, so the alpha value will be 0.05. So any p-value, if the p-value is less than 0.05, then you can reject it. You can reject the null hypothesis of no relationship. Which means if it is a small value, it's unlikely that what you observe it is just by mere chance. Okay, there is actually a significant relationship. Again, for that confidence level. So hence the null hypothesis is rejected when the p-value is smaller than the alpha, and it is not rejected when it is greater than. So for the 95% confidence level, again, if the p-value is greater than 0.05, then you cannot reject it. You cannot reject the null value, so basically it is statistically insignificant. So until this point, we talked about how we estimate the parameters using least square, how to put confidence interval in the estimated quantities, and then how we perform significant tests on the estimated quantities, on the estimated parameters. Here we talk about model accuracy. That means how accurate the model is, and this is also called goodness of fit. That means on average how close we are, the estimated quantity is to the population mean. Okay. So usually, typically, it is assessed using two metrics, the residual standard error and the R-squared. Now, when we get to a multiple regression version of linear regression, we'll talk about another variant of R-squared called adjusted R-squared. which accounts for the number of predictors in the regression model. So the residual standard error is the average amount that the response will deviate from the true regression line. So you want this to be a small value, right? This on average how far you are from the regression line. So in a way, it measures the lack of fit. So the larger it is, the fit is not good. And it is calculated as a residual sum of a square divided by the degrees of freedom, which is the number of observation, the difference between the number of observation and the number of coefficients estimated. In our case, for simple linear regression, we have two: the intercept and the slope. You take the square root of that quantity, and that is how the standard error is the residual standard error is estimated. So again, from the previous slide, the residual sum of square is just the difference between the observed and the estimated. We take the square of the I, and we sum over and divided by the degrees of freedom. Now, although you know the smaller RAC is a good thing, it is not quite clear what is acceptable, right? That depends on the application. So there is no really any specific value you're after. Okay, another one is R squared. So unlike the residual standard error, this one measures the proportion of the variance explained by the model. Okay, that means it falls between the R squared falls between 0 and 1. So the total sum of a square, which is R squared, equals the total sum of a square, which is given here. That is assuming you don't have a model, null model, which is a simple, if you take the simple average of this response variable, minus the residual sum of square, which is obtained by fitting the linear regression, and you normalize by the total sum of the square. So that is R squared. So the higher the number the closer the R squared to 1 is an indication that the model is a good model. It was able to explain most of the variability in the response. Now, if it is not good, that means if it is close to 0, potentially two things. One is the actual fit is not a good fit, right? Maybe some of the assumptions are not met or violated, like there is a linear relationship between the predictors and the response variable, or the errors are uncorrelated terms. So maybe it's an indication of those assumptions not being met, or the variance, inherent variance, is large, rather like that. I discussed this earlier that there are two primary components of the error terms. One is the one that you can improve, that you can reduce by improving the feeding process and by picking the right algorithm. That's called reducible error. And there's another error, irreducible error, where it is there. Even if you have a perfect model, that error you cannot minimize, you cannot reduce. Okay, so it could be, if that error is so large, then the R squared tends to be, it gets close to 0 value. What we discussed so far is about simple linear regression, where you have a single regressor and a single response variable. Here, we'll discuss about multiple linear regression, which is nothing but an extension of a simple regression where you have multiple regressors, up to p regressors. Okay? And the form of the function is basically an extension. If you remember from simple regression, it was the population regression line was y equals beta 0 plus beta 1 times x1 plus error term. Here now we have additional terms for the additional predictors. Okay, so multiple regression is where you have two or more regressors. Okay, and really the rest of the function is similar to what we saw in the simple linear regression. So the beta j is, now the interpretation of a multiple linear regression is a little different from simple linear regression. If you remember earlier, so the beta 1 is the amount of change of the response variable as a result of a unit change in the x variable. But in multiple regression setting, you have multiple predictors, so you have to control for the additional parameters. So when you look at any given, the j is b, the beta term, the bj, the jth term of the beta, it is interpreted the average effect of on y for the unit change in the xj, keeping the other prediction constant, right? You have to control for the other variables. Okay. So the model, if you remember from simple linear regression, it was a line, and part of the estimation, the least square estimation, is by minimizing the error term, the difference between the observed value in the points on the line. Here, when we talk about multiple dimension, anything, we're talking about hyperplane. It's not a line anymore. For instance, here, a visualization for two explanatory variables and one response variable. So this is a three-dimensional plane. It's not a line any longer. Okay. So the least square minimizes the difference between any observed point and a point on the plane. Now, in higher dimension, it becomes very difficult to visualize this hyperplane, in that the concept extends, right? It applies still, although you can't visualize it, you can apply least square to minimize the observed value in the hyperplane, okay, the fitted hyperplane from the data. So again, least square is what is commonly used even for multiple linear regression. So you estimate the coefficients by minimizing the sum of the square of the residual. So the y value, difference between y's in the estimated hyperplane. Now, the form of this function involves matrix algebra manipulation. So I'm not going to go over the details of how the matrix multiplication is done or computed. If you're interested in any statistical book or linear regression, we'll go into the details of formulating, extracting the relationship between the matrix in the vector notation. So the key elements or important elements in multiple regression is, now since you have many variables as explanatory or predictors, are all or some of the predictors are related to the response variable. Okay, so part of determining that relationship involves multiple predictors and the goodness of fit of the model, which we have seen for single linear regression as well, and predicting the response for the set of the predictors that are included in the model. Like what we did for the simple linear regression case, we have to do hypothesis testing here as well for the multiple linear regression as well. And the formal test requires, and this is again the same assumption we've made for simple linear regression, the error terms are independent and they have constant variance. Okay. Now, the null hypothesis is a bit different from the simple linear regression case. In the simple linear regression, we say the null hypothesis is that the regressor is zero. So there is no relationship between the regressor and the response variable. Here, we have multiple predictors. So we're saying all the predictors, the corresponding beta values for all the predictors are zero. And then the alternative is at least one slope is non-zero. One of the coefficients are non-zero. Now, if the null hypothesis is true, the term, the sum of the square due to the regression, which is the difference between the total sum of the square and the residual sum of the square, those terms that we discussed in the simple linear regression, they follow a chi-square distribution, and they're independent from the sum of the residual sum of a square. And if the ratio of two independent chi-square random variables, each divided by the respective degrees of freedom If they follow an F distribution, then we can use F statistic for our hypothesis testing. And the F statistics is right here, which is the difference between the total sum of square and the residual sum of square divided by the number of predictors and over the residual sum of square over the degrees of freedom, which is n minus p minus 1. So if the null hypothesis is true, the numerator of the F statistics goes to it's the same as the variance. And if the linearity assumption is also true, is valid, and the denominator becomes the variance as well. And if there is no relationship, then variance over variance, the same variance, constant variance, becomes 1. So the F statistic gets close to 1. But when there is a relationship, the F will be greater than 1 because the numerator part of this F statistics will be larger than the variance. And in that case, there is a relationship and we can reject the null hypothesis. Now, I want to talk about the difference between the t-test and the f-test. Now, earlier we used the t-test to do the hypothesis testing of the parameter, the estimated parameter. So t-statistic test is the effect of a predictor is controlling for the effect of other predictors. So the beta values tell us whether the change in the response value as a result of a unit change of in the JS predictor, holding everything else constant, holding all the other predictors fixed. Okay, that's what the t-statistics tells us. So, but when you think about it, even when there is no true relationships, there is a small probability of some predictors with p-value 0. If you think about, let's say, if we have 100 predictors, so, and then if you do your hypothesis testing with 95% confidence, so there is a 5% probability at least one of the predictors is related, it's correlated. So you can see as the number of explanatory variables goes up, then the probability of one of them, even after we reject it using the t-statistic, the probability of by just a 5 probability chance of identifying one of the correlation to exist in the regression equation. So now the F statistic tries to account for the number of predictors are included in the regression equation. So with large number of predictors, this becomes an issue. They're using just the test statistic. So the F statistics is used to assess overall model performance, used to measure whether there is significant difference between the model prediction and the response in the simple average. And again, by accounting for the number of predictors included in the model. Now, similar to what we have for the t-statistic, where there is a corresponding p-value, we also have a corresponding p-value for the F statistic, which is an estimate of the probability that we would have observed the F statistics as large as what is estimated in our computation if the two variants are the same, right? So if that p-value is smaller, so it is unlikely that we would have seen a value that large in the F statistic. And the F statistic supplement is the t-test, and it doesn't suffer with larger predictors issue as it adjusts for the number of predictors. So the F statistic is usually in we'll see this later in this lecture. F statistic is used to measure the overall performance of the model, whereas the t statistics are for individual parameters or individual predictors. So the model fit. If you remember, we used R square earlier for the simple regression case, simple linear regression case. Now, In multiple linear regression, we have many predictors. So the nature of R squared is such that as we increase the number of predictors, the R squared gets better, even when the predictors are not really significant or are not strongly associated or correlated with the response variable. Just by the function of the formula in the R square, that R square gets better just when we increase the number of predictors. So it may not be a true measure in the multiple linear regression setting. So there is another one called adjusted R squared. So you need to use adjusted R squared in multiple regression setting. And is a modified R squared adjusted for the number of predictors. This is the formula, and the only difference here is we are taking into account the number of predictors, both in the residual sum of squares and the total sum of squares. It increases only if the new term improves the model more than would be expected by chance. So it is adjusting. Just because you add in a predictor doesn't result in increased adjusted R square unless there is a true relation between that predictor and the response variable. Which means it decreases when the predictor improves the model by less than expected by chance, and it's always lower than R squared. The maximum it can be is equal to the R squared. That means if there is a true relation between all the predictors, R squared would be the same as adjusted R squared. But otherwise, it will always be smaller than R squared because it will adjust, because of these terms here. Adjusted R squared can also be leveraged for overfitting issues. Now, I haven't discussed this point until now. Overfitting is a problem in data mining algorithms in general. It's not unique to regression problems. So what it means is the function that you fit, and we will discuss about overfitting. We will learn about overfitting in detail in subsequent lectures and subsequent modules when we learn about classification and the other supervised learning algorithms. So it is a condition where you fit a function, and that function is try to model all the noise in the data and the training data. In other words, it learns too much about the details of the training data, it doesn't generalize well. So when you apply, especially when you use this for prediction for future unseen cases, unseen observation, when you do prediction, it doesn't generalize well because it is too specific for that sample, for one sample. Okay, so adjusted R squared can be used to measure overfitting issues. So basically what you do is you take different number of variables and you fit model and you calculate the adjusted R squared. So when the adjusted R squared will be used as an indication if they are overfitting issues. That means you are including terms or variables that are not really useful for explaining for explaining the variance in the response. And we will have dedicated section on overfitting issues when we learn our first supervised learning algorithm. Model fitting in R. How do we fit linear regression in R? Now, this is not a lecture on R and how to use the linear model function in R, and I'm not going to go to the details of the parameters and the underlying implementation of the linear regression model in R. We will have a webinar tutorial on the package, as well as how to interpret models and how to set parameters. There's a detailed tutorial in this module. So this is just to go over some of the metrics and the statistics that we discussed in linear regression, both in simple and multiple regression, applying on a simple data set. So here I'm using data from US Census public use microdata sample pumps. If you're interested, it is a large number of variables. I am just using only two explanatory variable. In the application of this is for prediction to predict a household or a person income from demographic variables. So I'm limiting only to age and sex. And now I haven't discussed this well, except saying that the explanatory variables can be numeric or categorical variables, or a combination of those two, right? So here I have 6, which is a category, male or female. It's a binary variable. So the way you encode binary categorical variables in R or in linear regression is for each value. In our case, we have male and female. For just so those are levels of the categorical variable. You pick one reference level, and every other values will have a corresponding binary variable, 0 or 1 value, and their interpretation is in relation to the reference level. Here I'm using male to be the reference level, so it doesn't have its own variable, it's an explanatory variable. Only female has is included as predictor, but it is interpreted as well, its value is in relation to the reference level, which is male. So LM is the commonly used function in R. There is another called GLM, general linear models, which we won't get in here. That GLM is much more powerful. You can use it for including nonlinear terms and polynomial terms and things like that. But the LM, so the simple call that I'm making here is I'm passing the formula, which is the response variable or the target variable in followed by a tilde sign to separate the predictors from the response. The age and the sex is included here. So the data is a training data. Here I'm using a log transform, and I'll get into why I applied log transformation. In general, if you remember from your module 1 discussion, that sometimes you have to transform variables to have a better distribution of the variable. Here, the log is more or less a normal distribution or Gaussian distribution. And I will explain the effect of not transforming this variable later when I talk about a model diagnostics. Another aspect of not just unique to linear regression, but any supervised learning is to evaluate the model on it is generalization. You want to separate a training and the test data, and you fit the model using the training data, and you perform the actual evaluation on the test data. So that's a more realistic, unbiased estimation of the error that model makes, and it also helps mitigating the overfitting issue uh, uh, that I will discuss when we discuss issues related to linear regression. So here I call this function, and you fit the model. R does its own thing. It applies least square. Remember how the parameters are estimated using least square. And these are the results. So the residual is the distribution of the residual here. If you remember, one of the assumption of the residual is its mean is 0, and then it is normally distributed. So the median is close to the mean. So that you would expect this value to be close to 0. As for the coefficients or the parameters, here is, so we have two explanatory variables, NH6, and we have an intercept. So for the intercept, this is the beta 0, estimated beta 0. And for the age, this is a beta value for age, and this is another coefficient for the sex female, which is again in relation to the reference value of sex male. Okay. Standard error, another term that we discussed throughout this lecture, which tells you on average how much the estimation varies from the fitter line. So each of the estimated quantity will have a corresponding standard error, and the t-value is for the statistical test part. Using, remember, test, we use the t-statistic distribution, and the corresponding p-value is here. So for the 95% confidence, if the p-value is smaller than 0.5, which is the case here for all of these estimated parameters, then you are rejecting the null hypothesis of no relationship. So there is actual relation between the predictor and the response variable. So this is significance code in relation to how low the p-value is here, order of magnitude. Just explaining the stars here. So this section of the output model summary, by the way, you can get this by just calling the summary function on the fit model. Again, this aspect of how to do R will be explained in the R tutorial by the TAs. So this section of the summary of the model refers to the overall model, not individual parameters or individual predictors. So the residual standard error is 0.315, and this is overall residual error, and this is a decrease of 592 degrees of freedom. If you remember, the degrees of freedom is the difference between the number of observations you have in the number of predictors or the number of estimated parameters. And here, multiple R squared, this is another thing that we discussed, is this is the amount of variance that was explained. In this case, it's not a good number. As you can see, just 0.08. And part of the reason is because I didn't include, this is a very simplistic fit using only 2 variables out of many variables in the dataset, just for me to be able to explain some of the parameters that we discussed in this lecture. So adjusted R square again is one when you have multiple multiple linear regression, you have to adjust the R square to make sure that the R square you see is as a result of meaningful relation between the predictors and the response, not just a mere chance or just for the fact that you included another term in the equation. The F statistic is another important term for overall performance of the model, which is high. If you remember, higher values, larger values than 1 as an indication is overall there are significant predictors, or the variance explained by the model is large or higher. Okay, and then this is degrees of freedom, and this is a corresponding p-value for the F statistic, which is again very small. For the 95% confidence, this is much smaller. So that means overall this model is a good model, or it's unlikely we have gotten a value this large by chance. Okay, now we move to some potential issues that you might encounter or you need to consider when you work with linear regression model. Okay. And this is of less a concern in general for some of the latest techniques of machine learning algorithms that make a lot smaller number of assumptions than classical methods like regression. So the first one is non-linearity. Among other assumptions that we made, one of the main assumptions we did is, for the most part, there is a linear relationship between the predictors and the response variable. Okay. Again, that in multiple regression, the linearity is in the parameters. You can have other terms like non-linear terms in the explanatory variables, but they're still linear in the parameters. But if that relationship is strongly nonlinear, now even when very, very rarely you have uh, a relationship purely linear, but linear regression still works fine if it is not overly nonlinear. So if you have a strongly nonlinear estimation, then the model won't be accurate. Okay, so you're violating the term based on which linear regression was built, and it won't be a good fit. Now, in general, you use a residual plot is a type of model diagnostic, one of the plot that is used for diagnosing uh, the model fit or the assumption, the inherent assumption that exists in linear regression. So here I am using the fitted values. This is by default. If you just call a plot function on the model, you'd get 4 different charts, graphs, and this is one of the the residual plot is the most important one. So a fitted value again is the residual. So if there is no correlation, I mean if there is no linearity, then you will see some pattern here. But here, for the most part, the red line is kind of flat and the points are randomly scattered, around this line. So that means the linearity assumption we made for this is good. So there is no overly non-linear term. It's not a perfect line, but close enough that linear regression can be useful here. Now, I was able to get this by using a log transform. If you remember, my fit is transforming the response variable. So one of the things is nonlinear transformation of the predicate can help me to get this particular issue. If I didn't transform it, I think I'll probably have another chart that will show that. Another important assumption that we made is there is no correlation between the error terms, which is an important assumption. If the errors are correlated, however, now you would have unrealistic confidence in the model because the estimated standard errors will tend to underestimate, right? Because of the correlation between the error estimate, you get actually a small values than what would typically be, right? If the error terms were not correlated. So that is, wrong value. P-values will be lower, resulting in wrong significance conclusion. Some of the p-values will be small because of error correlation, when in reality they are larger, or in some cases there might be a value that you won't be able to reject the null hypothesis. And also the confidence interval will be narrower. That means the uncertainty, wrongly assumed the uncertainty is small when you should have a larger confidence interval. And overall, it will lead to kind of wrong confidence in the model because you underestimate the standard errors in the confidence levels, the confidence interval. So that's a very important assumption in regression is the correlation term should be independent. Now, in time series, how do you identify if there is correlation terms? So in time series data, the data is time series data. Time series data is the data where you measure the quantity as a function of its previous values, right? But sometime unit t. So in time series data, it is relatively easier to identify the correlation error term by looking at adjustment. So if the adjustment values are very close to each other, so they move together, then that's an indication of error term, correlated error terms. When you have non-time series data, and if the observations are not truly independent, they could lead to correlation between the error terms. So the important thing is, it is one of the critical assumptions in linear regression is that the error terms are uncorrelated. Another issue that you have to be familiar with and check for is heteroscedasticity issue, where Basically, it means we assume that the variance doesn't change with the value of the response. Okay. Um, so heteroscedastic refers to a non-constant variance of the error terms. So basically the variance increases the response. And in one, so the validity of the confidence interval, the hypothesis, the standard, all depend on this assumption. So here, again, using um, um, the plot, the residual plot, feeder values versus the residual. As you can see, to a smaller towards the smaller values of the response, the variance is small. But as you go further, as the values of the response goes up, the variance increases. So there is a variation of the points of scatter that have different, larger distances from this line. So as you go further, you see this funnel shape. In general, you would see that funnel shape if there is heteroscedasticity issue in the response. And this one, actually, earlier I was in my feed, I applied a log transform in response before I feed them. Here I removed that transform, and then that's what resulted in here. So a residual plot is used to identify heteroscedasticity. And again, like I said, the funnel shape is an indication of that. Transformation will help. Okay. Outliers and leverage points, and this is also a very important thing in linear regression. And again, we covered this in module 1. What is considered outliers? It's not always clear, but there are some guidelines. But an outlier is an extreme value, which is much different from the rest of the observation. And a data point with a response value much different than the general trend of the data. So if you have one point much farther, in some cases, depending on is that the x value or the y value, that's largely responsible for the fact that that outlier is far from the rest of the data, dictates what part of the model fitting is affected, either the fit or actually the parameters itself. So outliers typically don't have much effect on least squares. So if the outliers are due to a large value on the response, the effect you'll see is on the residual standard errors and on the R square, not on the actual fit. So the fit will probably stay the same, but when you calculate the residual error in the R square, they are affected. You can use box plots, scatter plots to identify outliers. Again, there is no hard and fast rule, but in general, 3 to 4 standard deviation away from the mean is considered outlier. If the value is that far from the mean of the distribution, then this is in general considered outlier. And knowing the reason for the outlier is important. If you know it was made by error, data entry error, then you can safely disregard that. But if it is a systematic indication of the system, whatever domain that data is from, so you might want to pay very close attention to why you have that value. It might be an indication of some failure of a system, some underlying issue. So you can't always ignore an outlier. So another variant of an outlier is a leverage point. This is just type of outlier where the x value is large. That means x value is much different from the rest of the data. In that case, it will influence the fit. So sometimes even when there is no linear fit, it might influence the fit such that it will make it look like there is a linear relationship between the predictors and the response variable, even when there is not. Sometimes only one outlier can make it look like there is a relationship. And it's easier to identify in simple linear regression where you have one variable because you can work with pairwise correlation. And in the case of multiple linear regression, you can use a leverage statistics to determine if there is leverage point. Another important issue that you have to be familiar with is collinearity, and it refers to the presence of correlated predictors. So basically, in your model, if some of the predictors are correlated to each other, so some of the estimation that you make might not be accurate, because it is kind of difficult to separate the effect of one variable on the response from the other, because they kind of move together, right? They are correlated. And it leads to reduction in the accuracy of the parameter estimates. Again, like I said, because you cannot untangle the effect of one variable on the response without the effect of another, because the explanatory variables are correlated. And they increase the standard error, um, and it reduces ability to correctly detect an n0 coefficient. Okay. A simple detection method is, again, this is for pairwise correlation, is a correlation matrix. You can use just pairwise, calculate for every variable pair, you can calculate the correlation, the matrix, and the correlation matrix will capture that. But for multi-collinearity, that means when in multiple variables, if there is a correlation among multiple variables, then you use a variance of inflation factor, and you take the ratio of the variance of the estimator from the full model over the variance by just that estimated parameter. And a value of largest indicate collinearity. Removing correlated variables is a simple mitigation. So that's one way. If you know that the for instance, if two explanatory variables are strongly correlated, you can remove one of the variables that is less correlated with the response variable, and with simple mitigation. Okay, so those are the things that you have to be aware of and cognizant in estimating regression coefficients. So, and that these are some consideration that you have to make in using a regression function or a regression fit. So regression should be interpolation and not extrapolation. So what this means is you cannot use a linear regression that you feed for values of x's outside of the domain. It's just because the fit was determined by the domains of x, right? If you have a new observation whose x values outside of that range, you cannot use the function to estimate to use that variable. So you have to use it on the interpolation, not extrapolation. The relation between the variables and the predictors are not necessarily causal. They may be causal, but the only thing, even after determining the statistical significance of the relationship, what you're saying is there is a relationship between the regressors in the response variable. Whether that relation is causal, it requires additional study. When you have large number of variables, it is typically very challenging. You get into overfitting issues. And if I didn't say about overfitting is a case where you have a very complicated function, complex function, fitting on the training sample, but it doesn't generalize well for cases that it hasn't seen so far. So during actual use of the model, so you might get a wrong prediction. So when you have a large number of variables, one of the issue that you will face is overfitting. Also the same thing when you have categorical variables with many variables, like many levels, then that also presents challenge, because if you remember, one of the encoding scheme that we use for categorical variables is for each value of the predictor, we have a corresponding variable, binary variable. So we have a large number of categorical variable levels, then it is a challenge. Also, very large coefficients, the parameters, overly large standard errors, wrong sign are some indication of non-independence between the observations. Okay, and that's another assumption that the observations are independent. Model diagnostic and training is valid. So most of the things that we discussed so far at the residuals and things like that, they are based on the training sample. But also, it is a good practice to separate a test state where the test state means set of observations that did not contribute in the model fitting. So if you compute some of the statistics that we have discussed on the test, that is a better indication on an unbiased estimate of the corresponding metric using the test data. Lurking variables. So the model is as good as the number of variables you're able to include in the model. So if you avoid and exclude a variable that is very important for determining or predicting the response variable, then the model is not as good. It won't be as good because that variable is not included. So those are lurking variables, those that are not among the explanatory variables. Okay, so that's some of the considerations in linear regression.